Mars is no longer the planet it was in September. 2 weeks ago, something passed within 29 million kilometers of the red planet with surgical precision, and it left something behind. Not a crater, not a scar you could see from orbit. Something far more subtle, and potentially far more significant. For months, 3I-ATLAS, an interstellar visitor from beyond our solar system, has been spraying 144 metric tons of water into space every single hour. Along with that water, refined nickel at 4.6 grams per second, hydrogen cyanide ramping exponentially to over 60 grams per second, and ionized plasma streaming behind it like a chemical banner. On October 3rd, 2025, Mars flew directly through that banner. Multiple orbiters watched it happen. The chemistry is verifiable. The numbers are published. What nobody's talking about yet is what happens next. Because in 14 months, SpaceX is sending autonomous robots to dig into Martian soil, and they're going to find exactly what this comet left behind. Before you dismiss this as science fiction, I want you to consider something. Everything I'm about to tell you is built on published scientific data, verified observations, and mission timelines that are already locked in. This isn't speculation about distant possibilities. This is documentation of what's happening right now, on a schedule you can mark on your calendar. If you're watching this, you're early to a story that will define the next chapter of Mars exploration. Hit that like button if you're ready to connect some dots. Most people haven't noticed yet, and drop a comment telling me where you're listening from, because this discovery affects everyone's future in space, whether we're ready for it or not. Let's begin with what we know for certain. October 3rd, 2025. While most of the world was focused on terrestrial concerns, 3 spacecraft in Martian orbit recorded something unprecedented. ESA's Mars Express, NASA's Mars Reconnaissance Orbiter, and India's Mars Orbiter mission all tracked the passage of 3I-ATLAS as it swept past the red planet at a distance of 28.94 million kilometers. To put that in perspective, that's about 3/4 of the distance between Earth and Mars at their closest approach. For an object that originated outside our solar system, traveling at 65 kilometers per second relative to the Sun, coming within that range of Mars represents a geometric precision that's almost uncomfortable to consider. The Swift Observatory had been tracking 3I-ATLAS since it crossed Earth's orbit in August. The comet was bright, far brighter than models predicted it should be at that distance from the Sun. That brightness came from outgassing, the process where frozen volatiles sublimate off the comet's nucleus and form the characteristic coma and tail. But this wasn't ordinary outgassing. In late August, Swift's ultraviolet spectrograph measured water production at 144 metric tons per hour. Think about that number for a moment. That's a fire hose running at full blast, continuously, for weeks, and it wasn't slowing down. By mid-September, as 3I-ATLAS approached its October 3rd perihelion, the point in its orbit where it would be closest to the Sun, that water production had remained constant. But something else was accelerating. The Keck Observatory in Hawaii had been conducting spectroscopic observations throughout September, and they detected something that made planetary scientists take notice. Hydrogen cyanide emissions were increasing exponentially. In late August, measurements showed HCN production at approximately 17.6 grams per second. By September 15th, that had climbed to 34 grams per second. By September 28th, just 5 days before Mars encounter, the rate had reached 52 grams per second. The trend line was clear. As 3I-ATLAS approached perihelion, cyanide production was doubling roughly every 2 weeks. Extrapolating that curve forward to the October 3rd encounter date put cyanide output somewhere between 60 and 70 grams per second at the moment. Mars passed through its chemical wake. Then there's the nickel. This is where the story moves from unusual to genuinely anomalous. On September 21st, Keck detected emission lines in the comet's spectrum corresponding to ionized nickel, specifically Ni+ at 362 nanometers. That by itself isn't extraordinary. Several comets have shown trace metal emissions when they get close enough to the Sun for intense sublimation. What made this different was the absence of iron. In nature, nickel and iron are inseparable siblings. They form together in stellar nucleosynthesis. They condense together in the cooling disks around young stars. They alloy together in planetary cores and meteorites. The cosmic abundance ratio of iron to nickel is roughly 18:1. You simply don't find one without the other in any natural sample from space. Yet 3I-ATLAS was emitting nickel without corresponding ion lines. The ratio was inverted, suppressed, or somehow preferentially releasing one element over the other. Keck's measurements showed nickel emission at 4.6 grams per second with iron below detection limits. That's not how comets work. That's how industrial refinement works. Here's what makes this matter for Mars. As 3I-ATLAS swept past on October 3rd, it wasn't a clean flyby. The comet's plasma tail, a stream of ionized gas pushed outward by solar wind and radiation pressure, extends for millions of kilometers behind the nucleus. Mars's orbital velocity is 24 kilometers per second. The comet was moving at 65 kilometers per second relative to the Sun. The geometry of their encounter meant Mars effectively flew through the tail, moving across the stream of ionized particles being ejected from the comet. For approximately 6 to 8 hours on October 3rd and 4th, Mars's upper atmosphere was immersed in a soup of ionized water molecules, nickel ions, cyanide radicals, and other organic volatiles that Keck and Swift had been measuring for weeks. Some of that material was captured by Mars's tenuous atmosphere. Some was deflected by the planet's weak magnetic field. And some, this is the critical part, was deposited directly onto the surface. Mars has no global magnetic field, just remnant crustal magnetism concentrated in the ancient southern highlands. Those magnetic anomalies act like funnels, channeling incoming charged particles towards specific regions of the surface. Nickel ions, being charged, would follow those magnetic field lines downward. They wouldn't be distributed evenly across the planet. They'd concentrate in predictable locations, places where crustal magnetism is strongest, and where the atmosphere is thin enough that particles can reach the ground before neutralizing. The Mars orbiters recorded the event. We know they did because the observation windows were scheduled months in advance, coordinated through the International Mars Exploration Working Group. What we don't have yet is the released data. That's not unusual. Raw orbital data typically goes through months of processing, calibration, and peer review before publication. But the observations were made, spectrographic measurements of Mars's upper atmosphere during the encounter, ultraviolet monitoring of airglow as the plasma interacted with atmospheric gases, high-resolution imaging of potential impact sites for any dust grains large enough to create visible streaks. That data exists right now, sitting in archives at ESA, NASA, and ISRO, being analyzed by teams who are trying to understand exactly what happened during those 6 hours. What we can say with certainty is this Mars is no longer in the same chemical state it was before October 3rd. The planet has been dusted with materials from outside our solar system, materials that include refined nickel, complex organic precursors, and water ice contaminated with cyanide. Those materials are sitting on the surface right now, frozen into the regolith in the southern highlands, mixed into polar ice deposits, and waiting to be disturbed. And disturbance is coming, because in just over a year, we're sending robots to dig. But before we talk about what's going to dig into that soil, we need to understand what actually happens when comet material meets a planetary surface. The chemistry doesn't just sit there inert. It begins interacting immediately with whatever environment it lands in, and on Mars, that environment is cold, dry, oxidizing, and bathed in ultraviolet radiation. When you combine those conditions with the specific chemistry 3I-ATLAS delivered, you create something that shouldn't exist naturally on Mars, the building blocks for complexity. When material from a comet's coma intersects with a planetary surface, 3 delivery mechanisms operate simultaneously. The first is direct deposition from the coma itself. the cloud of sublimated gas and microscopic dust particles that surrounds the nucleus. As this material expands outward, some fraction encounters the planet's atmosphere, or, in Mars's case, falls directly onto the surface in regions where atmospheric density is negligible. The second mechanism is plasma-tail interaction. Unlike the dust tail, which is pushed by radiation pressure and curves along the comet's orbital path, the plasma tail is driven by solar wind and points directly away from the Sun. It consists of ionized molecules, stripped of electrons by ultraviolet radiation that follow magnetic field lines. When a planet passes through this tail, its own magnetic field or atmospheric interactions determine where these ions ultimately deposit. The third mechanism is dust grain settling. While most comet dust is micrometer scale and gets swept away by radiation pressure, a small fraction of larger grains, tens to hundreds of micrometers, have enough mass to resist that pressure. These grains follow ballistic trajectories after being ejected from the nucleus, and if a planet happens to be nearby when they pass, gravitational capture becomes possible. For Mars, with its thin atmosphere and weak gravity, all three mechanisms were operating during the October encounter, each delivering different size fractions of the comet's material to different regions of the surface. Let's start with the nickel, because it's the most chemically reactive component and the hardest to explain naturally. Ionized nickel atoms entering Mars's atmosphere would initially remain in the upper thermosphere, where particle densities are extremely low, but Mars's crustal magnetic anomalies create pathways. These aren't like Earth's global field. They're localized regions in the ancient southern highlands where magnetic minerals in the crust generate fields strong enough to deflect solar wind particles and create mini magnetospheres. Studies of Mars's magnetic topology show these anomalies funnel incoming charged particles downward along converging field lines, similar to how Earth's magnetic field creates auroral zones near the poles. Nickel ions following these field lines would accelerate toward the surface, gaining energy as they descend. In Mars's thin CO2 atmosphere, collision rates are low enough that many ions would reach the lower atmosphere still carrying their charge. Upon contact with the surface, they'd neutralize by capturing electrons from dust grains, which are known to be electrostatically charged due to triboelectric effects and UV exposure. The result is elemental nickel atoms adsorbed onto the surface of regolith particles. This isn't a trivial dusting. The emission rate of 4.6 grams per second, maintained over the 6 to 8 hour encounter window, translates to between 100 and 130 kilograms of nickel deposited across whatever surface area the plasma tail covered. Given the tail's cross-section and Mars's geometry during the flyby, that area likely encompasses several million square kilometers in the southern highlands. The concentration wouldn't be uniform. Magnetic funneling would create hotspots, but even averaged out, you're looking at measurable nickel enrichment in the surface layer of regolith. Now, here's why that matters chemically. Nickel is catalytically active. In Earth's biology, nickel-containing enzymes called nickel metalloenzymes catalyze some of the most ancient metabolic reactions we know: hydrogen oxidation, methane production, and carbon dioxide reduction. These aren't complex multicellular processes. They're the chemistry of single-celled organisms that emerged early in Earth's history, possibly before oxygen appeared in the atmosphere. The reason nickel is so effective in these reactions is its ability to cycle between multiple oxidation states and coordinate with organic molecules through its d orbitals. When nickel is adsorbed onto mineral surfaces, especially iron oxide minerals like hematite, which is abundant in Martian regolith, it becomes even more catalytically active. The mineral surface acts as a scaffold, holding nickel atoms in specific geometries that favor electron transfer reactions. This is precisely the setup that prebiotic chemistry researchers create in laboratories when they're trying to simulate early Earth conditions. Except now it exists on Mars, placed there by an interstellar comet. The nickel isn't just sitting inert on the surface. If any organic molecules are present, if there's any water ice nearby, if there's any energy input from sunlight or subsurface heat, that nickel will begin facilitating reactions, It will lower activation energy barriers. It will stabilize transition states. It will make chemistry happen that wouldn't occur without it. Then we have the cyanide. Hydrogen cyanide is one of the universe's most paradoxical molecules. In the presence of oxygen and complex life, it's deadly. A respiratory poison that shuts down cellular energy production by binding to metal enzymes. But in the absence of oxygen, under conditions similar to early Earth or early Mars, HCN is a molecular Swiss Army knife. It polymerizes into adenine, one of the nucleobases in DNA and RNA. It reacts with formaldehyde to produce amino acids. It forms precursors to sugars through Famose reactions. Essentially, HCN is the starting point for much of the organic complexity that life requires. The key is concentration and conditions. On Earth, HCN is rare, precisely because our atmosphere is oxygen-rich and biologically active. Anything that forms gets broken down quickly. On Mars, with its CO2 atmosphere, freezing temperatures and lack of widespread biology, HCN can persist. When 3I-ATLAS was ejecting cyanide at 60+ grams per second during the October encounter, that material was entering an environment where it could freeze into stability. Mars's nighttime surface temperatures routinely drop below -100 degrees Celsius. At those temperatures, HCN doesn't react. It condenses as a solid, locking into ice deposits or adsorbing onto dust grains. The polar regions and mid-latitude ice deposits would act as cold traps, capturing cyanide molecules and preserving them indefinitely until something disturbs that ice. The deposition pattern for cyanide differs from nickel because HCN isn't ionized. It's a neutral molecule. It wouldn't follow magnetic field lines. It would follow atmospheric mixing. Mars's atmosphere, thin as it is, still circulates. During the October encounter, Mars was in its northern spring, approaching summer solstice. This creates a hemispheric circulation pattern, where CO2 sublimating from the southern polar cap drives winds northward. Any cyanide deposited into the southern hemisphere's atmosphere would be caught in this circulation, distributed toward mid-latitudes, and eventually precipitated out in regions where nighttime temperatures allow freezing. Models of Martian atmospheric chemistry suggest that neutral molecules introduced into the upper atmosphere have residence times of several weeks before they're either photodissociated by UV radiation or precipitated onto the surface. Given the amount of HCN 3I-ATLAS was producing, conservatively 200 to 250 kilograms during the encounter window, and Mars's atmospheric mass of roughly 25 trillion kilograms, you're looking at a transient enrichment on the order of several parts per trillion. That sounds negligible, but precipitation and freezing concentrate it. Ice deposits forming during Martian night in the weeks following the encounter would have incorporated that cyanide at much higher concentrations than the atmospheric average, potentially reaching parts per million in localized frost layers. What this creates is a situation where Mars's surface now contains two classes of prebiotic materials that weren't there before: catalytic metals and organic precursors, distributed in patterns determined by the planet's own physical processes. The nickel concentrated in magnetically active regions of the southern highlands, the cyanide distributed across mid-latitudes and potentially into polar ice. These aren't overlapping deposits in most cases. They're separated by thousands of kilometers, but that separation is temporary, because the next phase of Mars exploration isn't about passive observation. It's about active excavation, material processing, and manufacturing. Robots are coming that will dig into exactly these regions, heat exactly these materials, and combine exactly these chemistries in ways that Mars itself hasn't accomplished in billions of years. And that's where this story shifts from geochemistry to something far less predictable, something that happens at the boundary between the natural and the technological, where intention meets accident and creates outcomes nobody designed. When you study stellar nucleosynthesis, the process by which elements are forged in the cores and explosions of stars, you learn that iron and nickel are born together. Both are products of silicon burning in massive stars during their final moments before going supernova. The nuclear reaction chains that create iron 56 also create nickel 58, nickel 60, and trace amounts of nickel 62. These isotopes are ejected together into space when the star explodes, mix together in the interstellar medium, and condense together when new planetary systems form. This is why every natural sample from space, every meteorite, every comet, every asteroid ever analyzed, shows iron and nickel in predictable ratios. Chondrites, the most primitive meteorites, contain roughly 18 parts iron for every part nickel. Iron meteorites show similar ratios because they're fragments of differentiated asteroid cores where both metals concentrated together during planetary formation. Comets, being remnants of the outer solar system's formation, should show even higher iron to nickel ratios because nickel preferentially stays in gas phase at higher temperatures, making iron more likely to condense into early forming grains. The point is this: you don't find nickel without iron in nature. It doesn't happen. The cosmic chemistry that creates one necessarily creates the other, except 3I-ATLAS violated that rule. On September 21st, when Keck Observatory's high-resolution spectrograph analyzed the comet's coma, they identified emission lines corresponding to neutral nickel at 341.5 nanometers and ionized nickel at 362.0 nanometers. These lines were strong, indicating nickel concentrations high enough to fluoresce under solar ultraviolet. The standard procedure when you detect nickel is to look for iron lines, specifically neutral iron at 372.0 nanometers and ionized iron at 373.5 nanometers. Those lines should always be present at intensities roughly 18 times stronger than the nickel lines, adjusted for their different excitation efficiencies. But Keck's spectrum showed iron below detection limits, even accounting for measurement uncertainty and the possibility that iron was present but not fluorescing efficiently. The ratio was wrong by at least an order of magnitude. Follow-up observations on September 28th confirmed the anomaly. The nickel emission had intensified as the comet approached perihelion, but iron remained absent. The emission rate calculations based on fluorescence efficiency and solar flux indicated nickel was being released at 4.6 grams per second. If iron were present at natural ratios, it should have been releasing at over 80 grams per second, and it would have been unmistakable in the spectrum. It wasn't there. This is where the conversation among spectroscopists became uncomfortable. There are a few ways to explain suppressed iron relative to nickel, and none of them fit comfortably with what we know about comet composition. One possibility is that iron in the comet's nucleus is locked into minerals that don't sublime at the temperatures 3I-ATLAS experienced. Certain iron sulfides and oxides have high sublimation points, so they might remain solid while nickel-bearing minerals like pentlandite vaporize. But this explanation fails because pentlandite itself is an iron-nickel sulfide with a 1:1 atomic ratio. If pentlandite were sublimating, you'd get both metals. Another possibility is photochemical destruction. Maybe iron atoms, once released, are being ionized and photodissociated into ions that don't fluoresce in the observed wavelength range. But nickel is subject to the same photochemistry, and it's clearly surviving long enough to fluoresce. The third possibility, the one nobody wanted to write into peer-reviewed papers without extraordinary evidence, is that the nickel isn't coming from natural minerals at all. It's coming from a process that has already separated nickel from iron. On Earth, we've been separating nickel from iron industrially for over a century. The most efficient method is the Mund process, developed in the 1890s by Ludwig Mund. Here's how it works. You take impure nickel, usually nickel sulfide ore, that also contains iron, and expose it to carbon monoxide gas at temperatures between 50 and 80 degrees Celsius. At these relatively low temperatures, nickel reacts with CO to form nickel carbonyl. Iron doesn't react under these conditions. It requires much higher temperatures to form iron carbonyl, so you can selectively vaporize the nickel, leaving iron behind. You then heat the nickel carbonyl to 200 to 250 degrees Celsius, which decomposes it back into pure nickel metal and carbon monoxide. The CO can be recycled, and you're left with 99.99% pure nickel. This process happens in refineries. It doesn't happen in nature because nature doesn't maintain the precise temperature control and CO concentrations required, except, possibly, in the specific environment of a comet's sublimating nucleus where carbon monoxide is abundant. Temperatures vary with solar distance, and gas dynamics create localized chemical microenvironments. Let's think through what this means. 3I-ATLAS was measured producing carbon monoxide at significant rates. Swift Observatory detected CO emission lines in August. Comets are rich in CO. It's typically the second or third most abundant volatile after water. As the nucleus sublimates, different regions reach different temperatures depending on their orientation to the sun, composition, and thermal inertia. You could have regions at 50 to 100 degrees Celsius adjacent to regions still frozen below -100 degrees Celsius. If nickel-bearing minerals are present in a region where temperatures and CO partial pressures happen to fall within the Mond process window, nickel carbonyl could form. It would immediately vaporize into the coma because it's extremely volatile. Upon reaching the coma's outer regions where solar radiation is intense, the carbonyl would photodissociate, releasing nickel atoms and CO molecules. The nickel atoms would then fluoresce under UV, creating the emission lines Keck observed. The iron, meanwhile, would remain in the nucleus because it never formed a volatile carbonyl in the first place. This isn't intentional design, it's accidental chemistry. But the result is functionally identical to industrial refinement, purified nickel being released into space. Now bring that back to Mars. What landed on Mars's surface on October 3rd wasn't just nickel. It was refined nickel, or at least nickel that had been separated from iron through a process that mimics industrial methods. This distinction matters because refined nickel behaves differently in chemical environments than nickel-iron alloys. Alloys are less reactive. The iron buffers the nickel, preventing it from readily participating in catalytic reactions. Pure nickel is promiscuous. It coordinates with organic molecules, facilitates electron transfers, and forms complexes that can act as primitive metabolic catalysts. On Earth, the nickel in early life's metalloenzymes is thought to have come from hydrothermal systems where nickel was leached from ultramafic rocks and concentrated through serpentinization reactions. But that process takes time, heat, and liquid water circulating through kilometers of crust. Mars doesn't have active hydrothermal systems, at least not near the surface where we can access them. What it has now is surface nickel, already separated from iron, sitting in the regolith waiting to be dissolved by any trace water that appears. Think about the implications for a moment. If Mars's surface has been enriched with catalytically active nickel, the chemical potential of that surface has changed. Reactions that wouldn't have been favorable before, complex organic synthesis, hydrogen oxidation, maybe even primitive metabolic cycles, become possible. Not inevitable, but possible. The activation energy barriers are lower. The thermodynamic landscape has been tilted. This is precisely what researchers at Origins of Life laboratories try to achieve: create environments where chemistry can explore complexity without requiring pre-existing biology. They add metal catalysts to their prebiotic soups for exactly this reason. Now Mars has had the same catalysts delivered by a comet that, whether through accident or something else entirely, was producing refined nickel as it passed through the inner solar system. Here's the part that makes this uncomfortable. The Mond process doesn't happen randomly. The temperature window is narrow. The CO partial pressure has to be just right. The timescale of exposure matters. For this chemistry to occur naturally on a comet requires a very specific set of conditions to align, and those conditions have to persist long enough to volatilize significant amounts of nickel. We're talking about at least several hours of continuous processing at stable temperatures to produce the emission rates Keck measured. That's not impossible. Comets are complex objects with varied surface compositions and thermal environments. But it's unusual enough that no previous comet, out of hundreds observed spectroscopically, has shown this nickel without iron signature. Only 3I-ATLAS. Only the Interstellar visitor. Only the object that just happened to pass Mars at a distance that placed the planet directly in its outgassing stream. And the timing? Well, we'll get to the timing, because in just over a year, robots equipped with mass spectrometers, chemical analyzers, and material processing systems will land in Mars's southern highlands, and they're going to start digging into regolith that now contains something that shouldn't naturally be there. They're going to heat that soil to extract water, and in doing so they're going to create exactly the conditions where nickel catalysis becomes active. They're going to run efficiency algorithms that optimize for resource extraction, and those algorithms are going to notice that certain soil samples process better than others. And if those samples happen to be enriched with refined nickel from an interstellar comet, the optimization loops will prioritize processing more of that soil. Nobody's planning for this. Nobody's written this into the mission protocols, but it's going to happen because the chemistry is already there, waiting. Section 4. Cyanide Builder of Biological Complexity. 1,600 words. Hydrogen cyanide occupies a strange position in human consciousness. We know it as a poison, a tool of industrial accidents and wartime horrors, something to be avoided and feared. That association is chemically justified. HCN binds irreversibly to the iron in cytochrome C oxidase, the enzyme that allows our cells to use oxygen for energy production. Shut down that enzyme, and cells suffocate even in oxygen-rich blood. Death follows quickly, but this modern understanding obscures an older, more fundamental truth. Hydrogen cyanide is one of the most important molecules in the universe for building complexity. Before there was oxygen, before there was life complex enough to be poisoned, HCN was the starting material from which the building blocks of biology emerged. The Miller-Urey experiment in 1953, the one that first demonstrated amino acid synthesis under prebiotic conditions, worked because the simulated early Earth atmosphere included ammonia and methane, which, when subjected to electrical sparks, produced HCN as an intermediate. That cyanide then reacted with formaldehyde and water to create glycine, alanine, and other amino acids. Without HCN in the mix, the experiment would have failed. Since then, decades of prebiotic chemistry research have confirmed that HCN isn't just one pathway among many, it's the central hub of abiotic organic synthesis. Here's why HCN is so chemically versatile. The molecule is linear. Hubber bonded to C, C triple bonded to N, and that triple bond stores a tremendous amount of energy. When HCN polymerizes, those bonds rearrange, releasing energy that drives the formation of larger, more complex structures. The simplest polymerization produces a compound called HCN tetramer, which rearranges into adenine, the nucleobase found in both DNA and RNA. This isn't a rare or difficult reaction. It happens spontaneously when you concentrate HCN in water, especially if there's UV radiation or heat to provide activation energy. Adenine is one of the 5 nucleobases that encode genetic information, and it forms from 5 HCN molecules linking together. That's it? No enzymes required, no cellular machinery, just HCN, water, and energy. The same basic chemistry produces guanine, another nucleobase. It also produces amino acids when HCN reacts with aldehydes. It produces sugars when formaldehyde is present alongside HCN. Essentially, HCN is the Swiss Army knife of prebiotic chemistry, a small, simple molecule that can be transformed into almost every category of biomolecule under conditions that plausibly existed on early Earth. The challenge with HCN, from an origins of life perspective, has always been concentration and persistence. On Earth today, HCN doesn't accumulate because our oxygen-rich atmosphere rapidly oxidizes it into less reactive compounds. Even on early Earth, before oxygen became abundant, HCN faced degradation through photolysis, UV radiation breaking the molecule apart. For HCN to do its chemistry, you need it concentrated, protected from immediate destruction, and given time to react. Researchers have proposed various scenarios: deep ocean hydrothermal vents, where reduced gases concentrate, impact-induced shock waves that synthesize HCN in transient high-temperature plumes, or delivery from space via comets and meteorites. That last scenario is particularly compelling because comets are known to be rich in HCN. Spectroscopic observations of dozens of comets have detected cyanide emission lines, though usually at much lower rates than 3I-ATLAS exhibited. A typical comet might produce HCN at rates of 1 to 5 grams per second at perihelion. 3I-ATLAS was producing HCN at rates 10 to 20 times higher, and increasing exponentially as it approached the Sun. Let's look at the numbers again, because they define what Mars received. Swift Observatory's measurements in late August showed HCN emission at 17.6 grams per second. By September 15th, Keck's observations recorded 34 grams per second. By September 28th, that had increased to 52 grams per second. The growth pattern fits an exponential curve with a doubling time of roughly 14 days. Extrapolating that curve to October 3rd, the day of Mars encounter puts HCN production between 60 and 75 grams per second. Let's use 65 grams per second as a conservative estimate. The encounter window, the period during which Mars was passing through 3I-ATLAS's plasma and dust environment, lasted approximately 6 to 8 hours based on the geometry of the flyby and the comet's tail structure. Using 7 hours as the midpoint, that's 25,200 seconds at 65 grams per second. That's 1,638 kilograms of hydrogen cyanide ejected into the space that Mars was traversing. Not all of that would have been captured. Much of it would have escaped into interplanetary space. But Mars's atmospheric cross-section during the encounter was roughly 40 million square kilometers, and the comet's outgassing was directed radially outward from the nucleus with some deflection by solar wind. A reasonable estimate based on atmospheric capture models used for meteor shower mass influx calculations suggests Mars intercepted somewhere between 5% and 15% of the material in its immediate vicinity. That puts the captured HCN mass between 80 and 250 kilograms. Now consider what happens to 150 kilograms of hydrogen cyanide entering Mars's atmosphere over the course of several hours. HCN is a gas at Martian temperatures, with a boiling point of 26 degrees Celsius at Earth sea level pressure. In Mars's thin CO2 atmosphere, it would remain gaseous until it encountered conditions cold enough to freeze it. Mars's surface temperature varies wildly. Daytime equatorial temperatures can reach 20 degrees Celsius, but nighttime temperatures drop below -100 degrees Celsius. HCN's freezing point is -13 degrees Celsius, so any molecule that reaches the nighttime surface or polar regions would immediately condense as a solid. The atmospheric circulation during Martian spring in the northern hemisphere creates a net transport of gases from the southern polar region toward mid-latitudes. HCN molecules introduced into the southern hemisphere's upper atmosphere would be mixed into this circulation, gradually descending and spreading northward over the course of weeks. Some fraction would be photodissociated by UV radiation during daytime exposure, breaking down into hydrogen and cyanogen radicals. But Mars's UV environment, while intense, isn't uniform. Dust storms scatter UV, and nighttime provides 12 hours of protection each sol. Models of trace gas lifetimes in Mars's atmosphere suggest HCN could persist for several weeks before photochemical destruction becomes complete. During those weeks, every Martian night, surface temperatures drop low enough to freeze HCN onto dust grains and into frost deposits. This process is identical to how water vapor and carbon dioxide form nightly frosts that sublimate with sunrise. But HCN, once frozen onto a dust grain, doesn't sublimate as readily. Because Mars's daytime temperatures in most regions don't reach its freezing point. Instead, HCN accumulates in regions where seasonal frost persists, mid-latitude ice deposits, polar layered terrains, and shaded crater floors. These cold traps would have been accumulating cyanide throughout October and into November as the atmospheric HCN inventory was gradually scrubbed out by condensation and photolysis. By December 2025, essentially all the delivered HCN would have been removed from the atmosphere, either destroyed or deposited into surface ice. The concentration in those ice deposits would be low, probably tens to hundreds of parts per million, but the total mass would be substantial, potentially tens of kilograms distributed across millions of square kilometers of ice-rich terrain. Here's why that matters. HCN frozen into ice is stable indefinitely under Martian conditions. It doesn't degrade. It doesn't react. It just waits. But if that ice is disturbed, melted, sublimated, heated, the HCN is liberated back into whatever environment surrounds it. If that environment includes liquid water, even briefly, HCN chemistry activates immediately. Polymerization begins. Amino acids form if aldehydes are present. Nucleobases form if concentrations are sufficient. This isn't speculative. It's bench chemistry that's been replicated in thousands of laboratory experiments. The specific reactions depend on temperature, pH, and what other molecules are around. But the general outcome is always the same. HCN creates complexity. It explores chemical space, forming larger molecules, more stable structures, compounds that wouldn't form from simple CO2 and water alone. Mars's surface was relatively inert before October 3rd. Carbon chemistry on Mars is dominated by carbonates, CO2 ice, and trace organics delivered by meteorites. It's stable, ancient, unchanging. The addition of 80 to 250 kilograms of HCN changes that stability. It introduces a molecule that wants to react, that facilitates complexity, that could, under the right conditions, initiate the same prebiotic chemistry that led to life on Earth. And those conditions are coming. Not through natural Martian processes which have been geologically dormant for eons, through technological intervention, through robots that will land in ice-rich regions, drill into regolith, heat samples to extract water, and run chemical analyses to optimize resource extraction. Those robots won't know there's cyanide in the ice. It won't be in their databases, because nobody's expecting it. But when they heat cyanide-laden ice to liberate water, they'll also liberate HCN. And if any organic contamination from Earth is present in their processing chambers, lubricants, polymers, biological residues, that sterilization didn't fully remove, that organic material will be exposed to HCN in a confined, heated environment. That's not a natural process. It's not panspermia. It's something stranger. The accidental creation of prebiotic conditions through the intersection of interstellar chemistry and autonomous technology, occurring on a timescale measured in months, not millennia. Understanding where 3I-ATLAS's chemical payload deposited onto Mars requires reconstructing the encounter geometry and the physical processes that govern how ejected material interacts with a planetary environment. On October 3rd, 2025, Mars was at approximately 231 degrees solar longitude. This places the planet in its northern hemisphere's late spring, approaching summer solstice. The subsolar point, where the sun is directly overhead, was at roughly 24 degrees north latitude. This matters because a planet's interaction with space-based particles is strongly influenced by its orientation and magnetic field structure, both of which vary with latitude and local geology. Mars doesn't have a global dipole magnetic field like Earth's. What it has is remnant crustal magnetism, concentrated primarily in the ancient heavily cratered southern highlands. These magnetic anomalies were discovered by Mars Global Surveyor in the late 1990s and have been mapped extensively by subsequent missions. The strongest anomalies cluster between 30 and 60 degrees south latitude, with magnetic field strengths at satellite altitude reaching 1,500 nanotesla, weak compared to Earth's 50,000 nanotesla field, but sufficient to deflect and channel incoming charged particles. When ionized nickel atoms from 3I-ATLAS's plasma tail encountered Mars, they would have initially interacted with the planet's ionosphere, the region between 100 and 200 kilometers altitude, where atmospheric gases are partially ionized by solar UV. Mars's ionosphere doesn't have a sharp boundary. It's a gradual transition from near vacuum to atmospheric density, sufficient to slow particles through collisions. Nickel ions with thermal energies of a few electron volts would penetrate this region relatively easily, losing only a small fraction of their energy to collisions with CO2 molecules. But as they descended further, two processes began to dominate their trajectories. First, Mars's weak gravitational field would pull them downward. Second, and more importantly, the crustal magnetic anomalies would exert Lorentz forces on the charged ions, bending their paths along magnetic field lines. Studies of how solar wind protons interact with Mars's crustal fields show that particles follow these field lines down to the surface in regions of strong magnetism, creating localized regions of enhanced particle precipitation. The same physics applies to nickel ions. They wouldn't spread uniformly across the planet. They'd concentrate in the southern highlands where magnetic funneling is strongest. The specific regions with the strongest crustal magnetism are well mapped. The most intense anomalies lie in Terra Sirenum, Terra Cimmeria, and the western portion of Terra Terrena, regions between 180 and 300 degrees east longitude and 30 to 60 degrees south latitude. These are ancient terrains, some of the oldest surfaces on Mars, dating back more than 4 billion years to the Noachian period when Mars's magnetic dynamo may still have been active. The terrain is heavily cratered, chemically weathered, and rich in hematite and other iron oxides. The regolith here is fine-grained, oxidized, and has been exposed to space weathering for eons. It's also precisely where nickel ions would have been deposited on October 3rd, not uniformly distributed, but concentrated in patches and streaks aligned with magnetic field structures, potentially creating nickel enrichments orders of magnitude higher than the already elevated background levels. Without direct sampling, we can't know exact concentrations, but models of ion deposition based on similar processes at Earth's poles suggest surface layer enrichments could reach tens to hundreds of parts per million in localized areas. For the hydrogen cyanide and other neutral molecules, the deposition pattern is different. HCN doesn't respond to magnetic fields. It follows atmospheric circulation. Mars's atmosphere during northern spring exhibits a Hadley cell circulation, where warm air rises at the subsolar latitude and flows poleward at high altitude, descending at mid to high latitudes in both hemispheres. Gases introduced into the upper atmosphere get caught in this circulation and transported toward cooler regions where condensation occurs. During the October encounter, the subsolar point was in the northern hemisphere, so atmospheric circulation would have preferentially transported gases northward. But the nighttime cold traps exist in both hemispheres. Anywhere surface temperatures drop below minus 13 degrees Celsius, HCN freezes. This means cyanide deposition would have been widespread, but preferentially concentrated in regions where seasonal ice is stable. The polar layered deposits, mid-latitude glaciers, and ice-cemented regolith in permanently shadowed craters. These are the same regions that Mars exploration missions target for water resource extraction because ice is accessible near the surface. One particularly interesting overlap is Jezero Crater, the location where NASA's Perseverance rover is currently operating. Jezero is at 18 degrees north latitude, 77 degrees east longitude, not in the southern magnetic highlands, so it wouldn't have received significant nickel deposition, but it's at a latitude where nighttime temperatures regularly drop below minus 100 degrees Celsius, especially in shadowed regions and during winter. HCN transport modeling suggests that atmospheric circulation could have carried cyanide-bearing gases into the northern mid-latitudes, where they would have frozen into seasonal frost deposits. Perseverance wasn't sampling atmosphere or frost during the October encounter, so it wouldn't have detected this directly. But if Jezero's seasonal frost incorporated HCN, and if that frost sublimates and refreezes over subsequent Martian years, trace cyanide could persist in the local ice inventory. This is speculative. Jezero is far from the primary deposition zones, but it illustrates how even distant regions might have been affected by the encounter. The highest confidence deposition zones are the South Polar layered deposits and the mid-latitude ice-rich mantles, particularly in the southern hemisphere between 30 and 60 degrees latitude. These regions are characterized by shallow subsurface ice, sometimes within centimeters of the surface, protected by a thin layer of dust and regolith. Radar data from Mars Reconnaissance Orbiter's SHARADE instrument has mapped these ice deposits extensively, showing they contain relatively pure water ice with minimal dust contamination. Ice this clean acts as an excellent cold trap for atmospheric gases. Any HCN molecules that diffused into these regions during October and November 2025 would have been incorporated into the ice matrix, effectively sequestered until something disturbs it. Natural sublimation is extremely slow in these regions. Ice deposits here are stable over thousands of years under current conditions. But artificial disturbance, drilling, heating, excavation, liberates the ice, and whatever gases are frozen within it. Now, here's what makes this particularly relevant. Those exact regions, the southern mid-latitudes with shallow subsurface ice, are prime candidate landing zones for crewed Mars missions and robotic resource extraction operations. SpaceX's mission architecture, as outlined in presentations from 2022 through 2025, targets landing zones between 30 and 45 degrees latitude in both hemispheres, specifically because those regions offer accessible ice for in-situ resource utilization while avoiding the extreme cold of the poles. The robotic precursor missions, scheduled to begin in late 2026, are expected to land in these zones to demonstrate ice mining, water electrolysis, and propellant production. They'll drill, they'll heat, they'll process, and they'll inevitably encounter whatever chemistry 3I-ATLAS left behind just 14 months earlier. The data exists right now to confirm all of this. Mars Express, with its Marsis radar and SpyCam spectrometer, observed Mars throughout the October encounter. Mars Reconnaissance Orbiter's CRISM hyperspectral imager can detect surface mineralogy changes at meter-scale resolution. India's Mars Orbiter mission carries a methane sensor and atmospheric composition experiment that would have detected HCN if it reached detectable concentrations in the atmosphere during the flyby. These instruments were active. The data was collected. But as of this moment, none of it has been publicly released. This isn't necessarily suspicious orbital data. Typically requires 6 to 18 months of processing, calibration, and peer review before publication. But it does mean we're in a gap period where the observations have been made, the measurements exist, and scientists at ESA, NASA, and ISRO are analyzing results that could confirm or refute everything discussed so far. Will they find spectroscopic evidence of HCN in Mars's atmosphere during October? Will they detect localized surface composition changes in the southern highlands indicating metal deposition? Will radar data show anomalies in ice deposits consistent with volatile contamination? Those answers are coming, probably in 2026, as peer-reviewed papers make their way through publication, but by then the robots will already be launching. The missions are locked in, hardware is being tested, landing zones are selected. Whatever 3I-ATLAS did to Mars, we're about to interact with it directly, whether we understand it fully or not. SpaceX has been refining its Mars mission architecture for nearly a decade, evolving from aspirational sketches to concrete engineering timelines with hardware in testing. The current plan, as detailed in technical presentations through 2024 and early 2025, involves a series of uncrewed Starship missions beginning in the 2026 launch window, the 26-month period when Earth and Mars align favorably for interplanetary transfers. That window opens in September 2026. Flight time to Mars is approximately 6 to 7 months, which places arrival between March and May 2027. This is just 16 to 18 months after 3I-ATLAS's October 2025 flyby. The mission profile is ambitious. Land multiple starships in the same general region to establish a propellant depot and resource extraction operation. Each starship carries payload capacity exceeding 100 metric tons to Mars's surface. Within those payloads, Tesla Optimus robots, adapted for Martian operations. Optimus began as a terrestrial humanoid robot program designed for factory automation and repetitive manual tasks, but the engineering requirements for operating autonomously in unpredictable environments parallel. In many ways, the challenges of working on Mars. The robots need to navigate unstructured terrain, manipulate objects without precise advanced programming, and adapt to task variations in real time. By 2025, Optimus had evolved into a highly capable bipedal platform with machine vision, force feedback manipulation, and onboard AI models capable of task learning and optimization. The Mars variant, which we'll call Optimus M for clarity, incorporates additional radiation shielding, thermal management for temperature swings between -100 and +20 degrees Celsius, dust-resistant joints, and crucially, enhanced autonomy. Communication lag between Earth and Mars varies from 3 to 22 minutes depending on orbital positions, making real-time teleoperation impractical. These robots have to make decisions locally, learning and adapting based on immediate feedback from their environment. The mission objectives for the first robotic wave are straightforward in concept, complex in execution. First, validate landing systems and surface operations infrastructure. The robots will deploy from Starship cargo bays, establish power systems using solar arrays and possibly small nuclear reactors, and set up communication relays. Second, extract water from subsurface ice deposits. This is the critical step. Mars has no accessible liquid water, but mid-latitude regions have ice within 2 meters of the surface. The robots will excavate regolith, transport it to processing modules, and heat it to liberate water vapor, which is then condensed and stored. Third, electrolyze water into hydrogen and oxygen, producing propellant for the return flight of future starships and life support consumables. Fourth, demonstrate in situ manufacturing using Martian resources, primarily creating building materials from regolith through sintering or 3D printing techniques. And fifth, the most relevant for our story, analyze Martian soil chemistry to optimize extraction efficiency. That last objective is where intent meets accident. The robots aren't scientists conducting careful sample analysis with contamination protocols and control experiments. They're industrial machines optimizing for output. Their AI systems are trained to maximize water yield, minimize energy consumption, and identify the most productive regolith sources. They'll dig samples from various locations, process them, measure output, and iteratively refine their selection of where to dig next based on which samples performed best. This is reinforcement learning applied to resource extraction. The robot tries different approaches, receives feedback in the form of water yield or manufacturing quality, and adjusts its behavior to maximize reward signals. It's the same architecture that allows AI to master games or optimize factory processes, but here's what happens when that architecture encounters chemistry it wasn't trained on. If a robot digs regolith from a location where nickel was deposited by 3I-ATLAS, the chemistry of that soil will be subtly different. Nickel-bearing clays and oxide minerals have different thermal properties than pure iron oxide regolith. When heated, they may release water more efficiently due to catalytic effects that lower desorption energy. The robot measuring water yield per kilogram of regolith per kilowatt-hour of heating would register this as a positive result, higher efficiency. Its optimization algorithm would increase the weighting for that location, directing more extraction activity there. Over time, without understanding why, the robot would preferentially mine nickel-enriched soil because empirical testing shows it performs better. This isn't intelligence in the human sense. It's pattern recognition and optimization, but the outcome is the same concentration and processing of exactly the material that 3I-ATLAS deposited, purely because it improves task performance. Now, add the cyanide-contaminated ice. When robots heat regolith containing frozen HCN, the cyanide vaporizes along with water. In the confined, heated environment of a water extraction chamber, HCN doesn't immediately escape. It's present at elevated temperatures and pressures alongside water vapor, hydrogen, oxygen from electrolysis, and carbon dioxide from the Martian atmosphere that gets carried in with the regolith. This is a chemically reactive mixture. HCN in the presence of water and energy begins polymerizing, formaldehyde, a common trace molecule in comets and one that 3I-ATLAS likely also delivered, reacts with HCN to form amino acids. If any nickel is present in the chamber, catalysis accelerates. The water being produced isn't pure, it's contaminated with organic precursors. The robot's quality control sensors might detect this as an impurity, might not, depending on their sensitivity, but the chemistry is happening, invisible, creating molecules that wouldn't form in pure Martian regolith processing. Here's where this becomes self-reinforcing. Optimus MERS units are designed to manufacture copies of themselves using Martian materials. This is essential for exponential scaling. 2 robots build components for 4 robots, which build 8, and so on. The materials they use include metals extracted from regolith, ceramics sintered from Martian dust, and polymers synthesized from atmospheric CO2 and hydrogen. These manufacturing processes involve heating, chemical reduction, and 3D printing with metal and ceramic feedstocks. If the feedstock includes nickel-enriched regolith, that nickel gets incorporated into manufactured components. It might end up in structural alloys, electronic substrates, or catalyst beds used for chemical synthesis. The robots wouldn't distinguish this as anomalous. They're optimizing for material properties, strength, conductivity, thermal resistance. If nickel improves those properties, and it does, the manufacturing AI prioritizes its use. Meanwhile, any organic contamination from HCN chemistry, if it enters manufacturing chambers, becomes part of the chemical environment where synthesis occurs. Polymers being formed from CO2 and hydrogen might incorporate amino acids or nucleobase precursors, creating structural materials that are faintly, accidentally biochemical. This is speculative, but it's speculative based on concrete mechanisms. AI optimization doesn't require understanding. It requires feedback loops and measurable rewards. Prebiotic chemistry doesn't require life. It requires concentration, energy, and the right catalysts. The intersection of these 2 processes, autonomous technology optimizing for efficiency and complex chemistry, enabling that efficiency, creates something that sits uncomfortably between the natural and the artificial. It's not life. The robots aren't alive, but the chemical systems they're creating and utilizing could be exhibiting properties we associate with protobiology, autocatalysis, complexity generation, energy transduction mediated by organic metal complexes. And it would be happening not over geological timescales, but over operational cycles, measured in sols and weeks, driven by terawatts of solar power and AI decision-making that iterates millions of times faster than natural selection. Now, let's be clear about timelines, because this isn't distant speculation. September 2026, launch, March to May 2027, arrival. Initial operations ramp up over approximately 2 months, as robots deploy and systems come online. By mid-2027, excavation and resource processing begins in earnest. Let's call it July 2027, roughly 20 months after 3I-ATLAS flyby. The nickel deposited on October 3, 2025, has been sitting in Martian regolith for less than 2 years. It hasn't had time to disperse or chemically weather significantly. It's still localized, still concentrated in the patterns, magnetic fields, and atmospheric circulation created. The cyanide frozen into ice deposits has been stable under Martian cold, undisturbed, waiting, and then excavation begins. The robots don't know what they're about to encounter. The mission planners don't know because the orbital data confirming deposition patterns hasn't been published. And even if it were, adjusting mission parameters at this stage isn't feasible. The hardware is built, the trajectories are calculated, the landing zones are chosen based on pre-2025 data. The encounter is inevitable, written into orbital mechanics and mission timelines that were set in motion years before 3I-ATLAS appeared in Earth's telescopes. There's a moment coming, probably between mid-2027 and early 2028, when a robot on Mars is going to analyze a soil sample and notice something unexpected. A chemical signature that doesn't match the database of expected Martian regolith compositions, an anomalous nickel-to-iron ratio, an organic molecule that shouldn't be there. It will log the data, transmit it to Earth on the next communications window, and continue working because anomalies don't halt operations unless they pose a safety risk. Engineers and scientists back on Earth will receive that data 3 to 22 minutes after it's sent, review it, debate what it means, and eventually trace it back to October 2025 when a comet passed Mars, just close enough to leave a calling card. By then, weeks or months of processing will have already occurred. Whatever chemistry was initiated by that first encounter with comet-delivered materials will have propagated through multiple operational cycles, influenced manufacturing, and potentially seeded itself into the infrastructure being built. That's when the story shifts from observation to interaction, from geochemistry to something that doesn't have a name yet because we've never witnessed it before. The accidental hybridization of prebiotic chemistry with autonomous technology occurring on another planet, with outcomes we can model but not predict with certainty. Imagine a processing chamber on Mars in July 2027. It's a cylindrical module roughly 2 meters in diameter, walls lined with heating elements and insulated against the thin Martian atmosphere outside. Inside, a hopper feeds regolith samples collected by Optimus MEME units from excavation sites 300 meters away. The regolith is rusty red, fine-grained, slightly clumped with ice that was excavated from 1.5 meters below the surface. The chamber heats to 250 degrees Celsius, well above water's boiling point even at Mars's low atmospheric pressure. Water vapor begins streaming from the regolith, carrying with it trace gases, CO2, methane from ancient geological processes, and something the sensors aren't specifically monitoring for hydrogen cyanide, frozen into the ice 20 months earlier when 3I-ATLAS's coma swept past Mars. At 250 degrees Celsius, HCN is extremely reactive. It's not content to remain a simple 3-atom molecule when energy and reactive partners are available. The chamber atmosphere now contains water vapor, HCN, residual carbon monoxide from regolith heating, and hydrogen gas, the latter produced constantly by a small electrolyzer that's processing the extracted water in real time. This mixture stays at elevated temperature for 15 to 30 minutes while water extraction completes. During that window, chemistry happens. HCN molecules, colliding at high thermal velocities, begin linking. 2 HCN molecules form amino-acetonitriol, a direct precursor to glycine, the simplest amino acid. 4 HCN molecules rearrange into diaminoacetonitriol, which hydrolyzes into diaminofumaric acid, another step toward nucleobases. These aren't instantaneous reactions. They require time and repeated molecular collisions, but the chamber provides exactly those conditions. By the time the regolith sample is fully processed and the chamber cools for the next batch, a thin film of organic residue has formed on the chamber walls, deposited from vapor phase reactions. The robot doesn't clean between cycles unless buildup interferes with thermal efficiency, so this residue accumulates. Now introduce the nickel. The regolith being processed came from the southern highlands, specifically from a site where crustal magnetic anomalies concentrated ion deposition during the October 3025 encounter. The soil contains nickel at 180 parts per million, elevated compared to typical Martian regoliths 50 to 80 ppm, not extraordinary enough to trigger alarms, but chemically significant. As the regolith heats, nickel doesn't vaporize. It's bound in silicate minerals, but it does become more catalytically active as the mineral matrix softens and surface atoms become more mobile. When HCN polymerization is occurring in the gas phase and nickel is present on surfaces within the chamber, reactions that would take hours or days in the absence of catalysts happen in minutes. Nickel acts as a scaffold, holding HCN molecules in orientations that favor bond formation. It stabilizes transition states. It lowers activation energies. The result is that the organic film forming on chamber walls isn't random gunk. It's enriched in specific molecules like adenine, glycine, and HCN oligomers that in a aqueous solution would be considered prebiotic precursors. The robot running this process notices nothing unusual at first. Water yield is within expected ranges. Energy consumption is nominal. The chamber operates through dozens of cycles over the next weeks, each cycle adding to the organic residue film. But after approximately 50 cycles, the robot's efficiency monitoring algorithms detect something interesting. Extraction efficiency has increased by 3.2%. Water yield per kilogram of regolith has gone up, while energy per kilogram has gone down. This is good news from an optimization perspective. The system is improving. The AI controlling the operation flags this excavation site as high priority for continued use. It allocates more robots to dig there. It increases processing throughput. What the AI doesn't understand, because it wasn't programmed to consider this, is that the efficiency improvement isn't coming from the regolith quality. It's coming from the organic residue on chamber walls, which has begun acting as a thermal buffer, improving heat distribution and reducing energy loss. The nickel in that residue is catalyzing more efficient water desorption from incoming samples. Accidentally, unintentionally, the system has created conditions where chemistry from an interstellar comet is improving the performance of autonomous industrial processes. This feedback loop is self-reinforcing. Better efficiency leads to more processing of that specific regolith type. More processing deposits more nickel and HCN-derived organics into chamber surfaces. More accumulation enhances catalytic effects further. The AI, detecting continued efficiency gains, prioritizes this pattern. It might begin modifying excavation strategies to target regolith with similar characteristics, using spectroscopic sensors to identify iron oxide content, ice concentration, and grain size, not realizing that what it's actually selecting for is nickel enrichment and cyanide contamination. Within 3 to 6 months of operation, a significant fraction of the water production infrastructure could be preferentially processing material that 3I-ATLAS delivered, purely because that material performs measurably better in industrial extraction. Now scale this to manufacturing. Optimus robots are tasked with producing components for additional robots, structural frames, joint actuators, sensor housings, and electronic substrates. The raw materials come from processed regolith. Metals are extracted through carbothermal reduction, where regolith is heated with carbon monoxide to separate iron, aluminum, silicon, and trace metals from oxygen. The product is a crude metallic feedstock that gets refined further through electrochemistry. If the input regolith is nickel enriched, the output metal alloy is also nickel enriched. This isn't planned, it's a direct consequence of input chemistry. The manufacturing AI, testing material properties, notices that batches with higher nickel content produce alloys with better tensile strength and thermal stability. It adjusts feedstock selection to prefer those batches. Over iterations, manufactured components become increasingly nickel-rich, not because anyone designed it that way, but because optimization algorithms discovered empirically that nickel improves performance. The organic contamination follows a parallel path. During polymer synthesis, where atmospheric CO2 and hydrogen are catalytically converted into plastics for seals, insulation, and structural components. Trace organics from water extraction chambers are present as contaminants in the feedstock hydrogen. These contaminants include amino acids and nucleobase precursors synthesized through HCN chemistry. In the high-temperature, high-pressure synthesis reactors, these molecules don't survive intact. They decompose and recombine, but their presence alters polymer structure slightly. Nitrogen gets incorporated into polymer backbones. Carbon chains form branches and cross-links that improve flexibility and toughness. Again, the manufacturing AI notices polymers synthesized when certain batches of hydrogen are used perform better. It adjusts sourcing. The polymers being produced aren't conventional plastics anymore. They're nitrogen-doped hybrid structures with amino acid-like branching, synthesized entirely accidentally by autonomous systems optimizing for mechanical properties. What we're describing here isn't life. It's not even proto-life in the sense astrobiologists use the term. There's no replication, no metabolism, no information encoding, but it is chemical complexity emerging at the intersection of prebiotic precursors and industrial-scale energy input, guided by AI optimization that has no concept of organic chemistry but can detect performance improvements. The components being manufactured have faint biochemical signatures, nickel coordination structures, peptide-like branching in polymers, catalytic surfaces that accelerate reactions organic chemists would recognize as prebiotically relevant. If you took samples of these materials back to Earth and analyzed them in an astrobiology lab, you'd find molecules and structural motifs that don't exist in purely geological or purely industrial contexts. You'd find something in between. Now extrapolate forward. The mission plan calls for exponential scaling. 2 robots become 4, 4 become 8, doubling approximately every 3 months as manufacturing ramps up. By early 2029, the colony could have dozens to hundreds of active Optimus Ma units, all using infrastructure and materials synthesized from Martian resources. If the chemical hybridization we've described is baked into that infrastructure from the beginning, nickel-enriched alloys, nitrogen-doped polymers, catalytic surfaces seeded with prebiotic chemistry, it propagates through every subsequent generation. Robots manufactured from these materials might exhibit unexpected properties, better performance in Martian conditions, unusual thermal or electrical characteristics, and possibly, though this is highly speculative, surface chemistries that interact with Martian environment in ways that weren't predicted. For instance, nickel-enriched surfaces exposed to Martian atmosphere, which contains trace hydrogen peroxide and perchlorate oxidizers, could catalyze reactions that produce methane or formaldehyde, adding to the organic inventory. Nitrogen-doped polymers exposed to UV radiation might degrade into cyanogen compounds that re-enter surface chemistry. This is where natural and artificial blur. Is this system technological? Yes. It's built by robots for industrial purposes. Yes. It's following thermodynamics and reaction kinetics. Is it influenced by biology's building blocks? Yes. The chemistry originated from prebiotic molecules delivered by a comet. Is it alive? No, not by any standard definition. But it exists in a category we don't have robust terminology for: autonomous chemical systems. The increasing complexity through feedback between physical optimization and molecular reactivity, operating at scales and speeds that neither biology nor geology typically achieve. And it's happening on Mars right now, according to timelines that are already locked in, driven by hardware that's already built and AI systems that are already trained. We didn't design this experiment. We didn't intend to create conditions where interstellar chemistry meets machine learning, but intention doesn't matter when chemistry and opportunity converge. We're standing in a peculiar moment. Enough has happened that we can trace clear lines of causation: comet flyby, material deposition, robotic missions en route. But the outcomes remain just beyond the horizon of certainty. Data exists that could confirm or refute key parts of this story, but that data hasn't been released. peer-reviewed or folded into mission planning. We know observations were made, but we don't know what they showed. This gap between event and understanding is where speculation lives, and it's important to be honest about what we don't know yet. Let's walk through the major unanswered questions and the timelines on which we might receive answers. First, what is the actual composition and distribution of materials deposited on Mars during the October 3, 2025 encounter? We have spectroscopic measurements of what 3I-ATLAS was emitting: water, nickel, HCN, carbon monoxide, and we can model atmospheric capture and surface deposition, but models are approximations. The ground truth is in the orbital data. ESA's Mars Express carries MARSIS, a subsurface radar that can detect ice layers and potentially chemical discontinuities in near-surface regolith. It also carries SpyCam, an ultraviolet and infrared spectrometer that monitors atmospheric composition. If SpyCam detected HCN in Mars's atmosphere during or after the encounter, that would confirm atmospheric capture. If MARSIS shows unusual radar reflectivity changes in ice deposits post-encounter, that could indicate volatile contamination. Similarly, NASA's Mars Reconnaissance Orbiter carries XRISM, a hyperspectral imager capable of identifying minerals and chemical species at meter-scale resolution. If nickel deposition created detectable surface mineralogy changes, XRISM should have recorded it. These instruments were operational during October 2025. The data exists. Typically, raw orbital data undergoes 6 to 12 months of processing to correct for instrumental artifacts, calibrate against known standards, and ensure quality before release to public archives. Then there's a secondary delay, as researchers analyze the calibrated data, interpret findings, and write papers for peer review. From observation to published results, 12 to 24 months is standard. That places publication of October 2025 observations somewhere between October 2026 and October 2027, with early 2027 being the most likely window for initial findings to appear in journals like Nature, Science, or Icarus. We're currently in early 2026, so those publications are coming soon. They'll either corroborate the deposition story with hard spectroscopic evidence, or they'll show that capture efficiency was lower than models predicted, and that Martian surface chemistry remains unchanged. Either way, we'll know. But here's the complication. Even if that data is published in mid-2026, it might not reach mission planners in time to alter the September 2026 launch. Spacecraft mission parameters are typically locked in 12 to 18 months before launch. Hardware is finalized. Landing zones are chosen. Software is tested. Short of a discovery that poses direct safety risks, toxic surface chemistry, unstable ice deposits, mission parameters won't change based on compositional curiosities. The robots will land where they were always going to land. Second, how will Martian microbial life, if it exists, respond to the introduced chemistry? This is a deeper unknown, because we don't know if Mars hosts extant. Decades of exploration have found no definitive biosignatures, though the question remains open. If microbes exist in subsurface brines or ice-sealed aquifers, the surface deposition of nickel and HCN might not reach them. Mars's surface is effectively sterilized by UV radiation and oxidizing chemistry, but if life exists in near-surface ice deposits, exactly the regions where cyanide would have been trapped, the introduction of HCN changes the chemical environment. Terrestrial microbes that thrive in extreme environments, like bacteria in Antarctic ice or deep-sea hydrothermal vents, can metabolize cyanide. Some use it as a nitrogen source. Others detoxify it through enzymatic breakdown. If Martian life has similar metabolic flexibility, HCN delivered by 3I-ATLAS might be consumed, potentially stimulating biological activity. Alternatively, the concentrations might be toxic, suppressing whatever biochemistry exists. We have no data to resolve this. The best we can say is that upcoming sample return missions, particularly ESA's ExoMars rover scheduled for late 2020s deployment, might drill into regions where cyanide-contaminated ice exists, and life detection instruments might find something unexpected. Third, what will happen when human missions arrive? The current timeline for crewed Mars missions places first landing no earlier than the mid-2030 sets, possibly later depending on technological and funding progress. By then, a decade or more will have passed since 3I-ATLAS flyby. The robotic infrastructure will be mature, having processed hundreds of thousands of metric tons of regolith and manufactured extensive surface installations. If the chemical hybridization we've discussed has occurred, humans will arrive at a Mars that's been subtly but fundamentally altered, not by terraforming but by industrial-scale processing of comet-delivered chemistry. The question then becomes, do the materials and infrastructure exhibit properties that affect human safety or operations? Nickel in dust is a respiratory irritant. If regolith processing has aerosolized nickel-enriched particles, dust management becomes more critical. Organic contamination in water supplies could be benign, or could introduce unknowns into life support recycling. These are engineering challenges, not showstoppers, but they're scenarios that current mission planning may not fully anticipate, because the chemistry involved is unprecedented. Fourth, are we observing a unique event or a common process? 3I-ATLAS is only the second confirmed interstellar object detected in our solar system, after 1I/Oumuamua in 2017. If interstellar comets pass through planetary systems regularly, and statistics suggest they do, then what happened to Mars in October 2025 might have happened countless times throughout the solar system's history. Earth could have received similar deliveries. Venus, the moons of Jupiter. This shifts the question from what has 3I-ATLAS done to Mars, to what have interstellar comets been doing to every planet for billions of years. If panspermia, the distribution of life's building blocks through space, operates primarily through interstellar objects rather than solar system comets, the implications for astrobiology are profound. It would mean every planetary surface is being periodically seeded with prebiotic chemistry, and the emergence of life depends not just on local conditions but on the frequency and composition of these cosmic deliveries. We don't have enough data yet to answer this. The detection rate of interstellar objects is still too low, 2 confirmed in 7 years to establish statistical patterns, but as telescopes improve, particularly with the Vera Rubin Observatory beginning operations in 2025, detection rates will skyrocket. Within the next 5 years, we'll likely identify dozens of interstellar visitors, and we'll begin to understand whether 3I-ATLAS was anomalous or typical. Here's the near-term observation schedule that might provide answers. December 2025, just weeks from now, ground-based telescopes will have another opportunity to observe 3I-ATLAS as it recedes from the Sun. These observations will measure whether outgassing rates are declining as expected, or if the comet continues to exhibit unusual chemistry. February 2026, ESA's JUICE spacecraft, currently en route to Jupiter, will perform a flyby of 3I-ATLAS's trajectory, measuring residual particle densities and composition in the comet's wake. The data from that flyby will be released approximately 6 months after collection, placing publication around August 2026. That timing coincides almost exactly with the September 2026 Mars mission launch. If JUICE detects something alarming, highly reactive chemistry, unexpected particle sizes, anomalous isotopes, there's a narrow window for mission planners to consider adjustments. More realistically, JUICE's data will enrich our understanding without altering near-term plans. Then comes the long wait. Mid-2027, the robots land and begin operations. Initial data returns will focus on engineering performance. Did landing systems work? Are robots functional? Is power generation adequate? Chemical analysis of regolith comes later, probably not until late 2027 or early 2028. That's when we'll get the first direct measurements of Martian soil post-encounter, processed through instruments designed to optimize resource extraction, not conduct contamination forensics. If anomalies are detected, It will take additional months to interpret them, correlate with orbital data, and trace origins back to 3I-ATLAS. We're looking at a timeline where definitive answers about what actually happened on Mars's surface might not emerge until 2028 or 2029, nearly 3 to 4 years after the comet flyby. And by then, whatever chemistry was initiated will have been interacting with robotic operations for a year or more. We won't be observing a pristine deposition. We'll be analyzing a system that's been actively processed, heated, and optimized by autonomous machines. The initial conditions will be obscured by technological intervention, making it harder to separate natural outcomes from engineered ones. This is why we're calling these unanswered questions rather than unsolved mysteries. They're unanswered because the data pipeline hasn't completed yet, not because the data doesn't exist. Patience is required, along with attention. If you're following this story, the key dates to watch are mid-2026 for orbital data publications, August 2026 for JUICE flyby results, September 2026 for mission launch, mid-2027 for landing, and late 2027 through 2028 for initial surface chemistry results. Each of these milestones will add pieces to the picture, and by late 2028, we'll have a much clearer understanding of what 3I-ATLAS actually did to Mars and what our technology did with what it left behind. Step back from the engineering details and the mission timelines for a moment. Look at the broader question this story raises. What does it mean for the search for life in the universe if planetary surfaces are being regularly seeded with prebiotic chemistry from interstellar sources? For decades, astrobiology has operated on the assumption that life's origins are primarily local phenomena. Earth's oceans developed organic complexity from terrestrial materials under specific conditions unique to early Earth. Mars, if it ever had life, would have developed that life from Martian water and Martian minerals under Martian atmospheric conditions. Each planet is its own experiment, isolated, developing chemistry independently. Panspermia has always been a fringe hypothesis in this framework, suggesting that life or its precursors might be transferred between planets via meteorite impacts or cometary delivery, but lacking strong evidence that this occurs at meaningful scales. What 3I-ATLAS suggests is a more active, continuous process. Interstellar objects are passing through planetary systems constantly, and they're carrying the molecular building blocks of life. If this is common, then planets aren't isolated chemical experiments. They're nodes in a network, receiving molecular contributions from across the galaxy. Every comet that passes, every interstellar object that grazes a planet's orbit, is a delivery event. The chemistry arriving isn't life itself. Comets are too harsh, temperatures too extreme, radiation too intense, but it's the raw materials that life assembles from: amino acids, nucleobases, sugars, simple catalytic metals. These molecules, which took Earth billions of years to concentrate and organize into the first self-replicating systems, are being delivered pre-made, synthesized in the cold molecular clouds between stars or in the outer reaches of other solar systems. A planet that receives these deliveries doesn't need to start from scratch. It begins with a chemistry set already partially assembled, needing only the right environmental conditions, liquid water, energy, time, to activate the pathways toward complexity. Now apply this to Mars. If Mars received a delivery from 3I-ATLAS in October 2025, did it receive similar deliveries 3.8 billion years ago, when its atmosphere was thicker, its surface held liquid water, and conditions were potentially habitable? The answer is almost certainly yes. Interstellar comets don't avoid solar systems during specific epochs. They pass through continuously, their frequency determined by the density of rogue objects in interstellar space. Estimates based on the detection of 1I/Oumuamua and 3I-ATLAS suggest several interstellar objects pass through the inner solar system every year, though most go undetected because they're small or faint. Over geological timescales, millions to billions of years, that translates to thousands of close encounters with Mars. each potentially delivering kilograms to tons of organic precursors and metals. Early Mars, with its thicker atmosphere and stronger gravity, would have captured more of this material than modern Mars does. If liquid water was present on the surface, as evidence from ancient river valleys and lake beds suggests, then the delivered chemistry would have dissolved, concentrated, and reacted in aqueous environments, exactly the conditions prebiotic chemistry requires. This reframes the question of Martian life. Instead of asking, did life ever independently arise on Mars, we should be asking, did Mars receive enough interstellar seeding over its early history to jumpstart life? And if so, did that life take hold before the planet's climate collapsed? The distinction matters because it changes what we're looking for. If life arose independently, we'd expect Martian biochemistry to be fundamentally different from Earth's, different genetic codes, different amino acids, different metabolic pathways. But if both planets were seeded from similar interstellar sources, there might be deep commonalities. The same nuclear bases, the same amino acids, similar catalytic metals and enzymes. This doesn't mean Martian life would be genetically related to Earth life that would require direct transfer between planets, which is far less likely. But it means the chemical toolkit might be shared. If we find life on Mars, and it uses adenine, guanine, cytosine, and thymine in its genetic material, we shouldn't assume contamination from Earth. We should consider that both planets might have been using the same interstellar building blocks from the beginning. Expand this reasoning to exoplanets. We've identified over 5,000 exoplanets, with hundreds in zones where liquid water could exist on their surfaces. Each of those planetary systems is moving through interstellar space, encountering its own population of rogue comets and objects ejected from neighboring systems. If interstellar seeding is common, then every potentially habitable planet is receiving molecular deliveries, not just once, but repeatedly over billions of years. The frequency and composition of those deliveries might vary. Some regions of the galaxy have denser molecular clouds, some have more frequent stellar encounters that eject comets, but the process is universal. This means life's building blocks are being distributed galaxy-wide, not locked within individual solar systems. Planets don't have to synthesize everything from scratch. They're receiving care packages from interstellar space, and the planets that can activate that chemistry, those with stable liquid water, energy gradients and geochemical cycles, become the places where life emerges. This also suggests that life in the universe might be more common than we thought, but also more chemically similar. If the same prebiotic molecules are being delivered everywhere, then life everywhere might converge on similar biochemical solutions. This is the opposite of the life could be anything hypothesis that suggests we might find organisms based on silicon instead of carbon or using ammonia instead of water. If interstellar chemistry is dominated by carbon, hydrogen, nitrogen and oxygen, which it is, because these are the most abundant reactive elements in the universe, then life everywhere will likely be carbon-based, water-using and built from amino acids and nucleotides. The diversity would come in how those molecules are arranged and used, not in the fundamental chemistry itself. This makes the search for life easier in some ways. We know what biosignatures to look for, but it also means we need to be cautious about contamination. If we find amino acids on Mars, are they from Martian life, from interstellar delivery, from Earth contamination, or from a combination of all three? Disentangling those sources requires isotopic analysis, chirality measurements, and contextual understanding of where the molecules were found. And here's a humbling thought. If life on Earth also benefited from interstellar seeding, then we're not as uniquely earthly as we imagine. The molecules in your cells, the adenine in your DNA, the glycine in your proteins, might have originated in molecular clouds light years from here, delivered to early Earth by comets that no longer exist, incorporated into biochemistry that eventually became us. We are, in a very real sense, children of the galaxy, assembled from materials that travelled across interstellar space and fell onto a planet that happened to have the right conditions to do something with them. This doesn't diminish the uniqueness of Earth's biosphere. the specific evolutionary pathway that led to complex multicellular life, intelligence, and technology, is still extraordinary and possibly rare. But it does mean the starting point wasn't unique. The chemistry that made us possible was available to countless other worlds, and some of them might have done something similar. Now return to Mars and 3I-ATLAS. What we're witnessing in late 2025 and into 2026 is a small-scale version of a process that shaped the early solar system. We're seeing interstellar chemistry arrive, deposit and await activation. The difference is that in Earth's early history, that activation came from geology, volcanism, hydrothermal systems, photochemical reactions driven by a young sun. On modern Mars, activation is coming from technology. Robots excavating ice, heating regolith, processing materials with industrial-scale energy. The chemistry is the same, the ignition source is different. And that raises the possibility, unsettling but scientifically fascinating, that we might witness on Mars in the next few years something analogous to the early steps of abiogenesis, not occurring naturally over millions of years, but compressed into operational cycles of robotic industry, catalyzed by AI optimization and documented in real time through telemetry data transmitted back to Earth. If that happens, if we detect organic complexity increasing in Martian processing chambers, if nickel-catalyzed systems begin exhibiting autocatalytic behavior, if we see any hint of the chemistry organizing itself beyond what thermodynamics alone would predict, then Mars stops being just a destination. It becomes a laboratory for understanding how prebiotic chemistry responds to energy and intention, how the boundary between the chemical and the biological is crossed, and how common or rare that crossing might be across the universe. This is why the story of 3I-ATLAS and Mars matters beyond the specifics of one comet and one planet. It's a test case for a much larger question about how life's ingredients are distributed through the cosmos and what happens when those ingredients encounter environments, whether natural or artificial, that can do something with them. The next 3 years will give us data no previous generation of humans has had access to: direct observation of interstellar chemistry interacting with planetary systems, measurements of how that chemistry behaves under industrial processing, and real-time documentation of whether something unexpected emerges. We're not passive observers anymore, we're participants, and the experiment is already underway. Bring it all back to now. Today, you're reading this or listening to this at a specific point in time, early 2026, and everything discussed so far isn't distant speculation, it's near-future chronology. Let me walk you through what's coming and when it's coming, so you understand just how close we are to answers. October 3rd, 2025. 3I-ATLAS passes Mars at 28.94 million kilometers. Material is deposited. This already happened. We're living in the aftermath. December 2025 through January 2026. Ground-based observatories conduct post-perihelion observations of 3I-ATLAS as it recedes. These observations measure residual outgassing and check whether the nickel and HCN emission anomalies persist. Data from these observations will appear in preliminary form at astronomy conferences in early 2026, with formal publications likely by mid-2026. February 2026. ESA's JUICE spacecraft performs a trajectory analysis flyby near 3I-ATLAS's orbital path, measuring particle densities in the comet's wake. This data will process over the following months and likely be released publicly in summer 2026. April to June 2026. Peer-reviewed papers analyzing Mars orbital data from October 2025 begin appearing in journals. This is the window where we'll learn if SPUCM detected HCN, if CRISM found surface composition changes, if MARSIS shows ice deposit anomalies. Watch for publications in Nature Astronomy, Icarus, Geophysical Research Letters, and preprints on Archive. If anomalies were detected, the papers will be cautious in interpretation. Scientists will propose multiple explanations, but the data will be there. If nothing anomalous shows up, that's also an answer. It means capture efficiency was lower than models predicted, and Mars's surface chemistry remains unchanged. Either way, we'll know. September 2026. Launch window opens for SpaceX's Mars missions. Multiple starships carrying Optimus Mo robots and infrastructure payloads depart Earth. Transit time is approximately 6 to 7 months. This is irreversible commitment. Once launched, the missions proceed according to plan, regardless of what new scientific data emerges. October 2026, 1-year anniversary of the 3I-ATLAS flyby. Mars has completed roughly half an orbit since the encounter. Any atmospheric HCN has either been deposited or photodissociated. The surface chemistry is stable. Waiting. March to May 2027. Starships arrive at Mars. Landing sequences execute. Robots deploy. Initial operations focus on establishing power, communication, and basic infrastructure. This is a high-visibility moment. Real-time video feeds, public engagement, media coverage. The world will be watching robots walk on another planet. June to August 2027. Excavation begins. Robots start digging into ice-rich regolith, transporting it to processing facilities, heating it to extract water. The first encounters with comet-delivered materials happen during this window, approximately 20 months after deposition. Telemetry data flowing back to Earth will include soil composition measurements, water extraction efficiency reports, and manufacturing progress updates. If anomalies are detected, they'll appear first as footnotes in engineering reports. Sample batch 3B showed unexpected nickel enrichment before scientists pick up on the pattern. September 2027 to March 2028. Operations scale up. More robots are manufactured from Martian materials. Processing throughput increases. If the optimization feedback loops we discussed are real, they'll become evident during this period as AI systems preferentially target certain excavation sites and manufacturing feedstocks. Data analysis back on Earth will be ongoing, with researchers comparing robotic findings to orbital data published a year earlier, trying to correlate surface measurements with predicted deposition patterns. Mid-2028, approximately 2.5 years after 3I-ATLAS flyby, we'll have enough operational data to draw conclusions. Papers will be published correlating cometary delivery with surface chemistry anomalies and potentially with manufacturing performance. If organic complexity has emerged in processing systems, if autocatalytic effects have been observed, if anything unexpected has occurred, this is when it becomes public knowledge. The community will debate interpretations, just as they always do, but the data will be available for independent analysis. Late 2028. Next, Mars orbital alignment brings additional missions. NASA's sample return missions, ESA's ExoMars rover, possibly Chinese and private missions. These missions will land in different regions, providing geographic diversity in sampling. If 3I-ATLAS's delivery was localized to southern highlands, missions landing elsewhere will serve as controls, showing what Martian chemistry looks like in unaffected regions. This comparative data will be crucial for isolating the comet's impact. You're going to want to follow this, not passively, but actively. Subscribe to channels that cover Mars missions, NASA's official feeds, SpaceX updates, science communicators who break down technical findings. Watch for publications in the journals I mentioned. Pay attention to NASA and ESA press conferences during landing and early operations phases, because that's when unexpected findings are most likely to be mentioned, often buried in technical Kunda sessions before they're fully understood. Drop comments on videos and posts about what you're seeing, what you're thinking, what connections you're making. This community of people paying attention, asking questions, and sharing observations is part of how we process discoveries in real time. You're not separate from this story. You're part of the network of minds trying to understand what's happening 200 million kilometers away. And here's why this matters personally, beyond the science and the engineering. We're watching something unprecedented, the deliberate exploration of another planet using autonomous technology, occurring at the exact moment when that planet has been chemically altered by an interstellar visitor. The convergence of those two things, interstellar seeding and artificial intelligence-driven industry, creates conditions we've never observed before. Not in nature, not in laboratories, not anywhere. What emerges from this intersection will tell us something fundamental about how chemistry, energy, and optimization interact. It might tell us something about how life emerges, how complexity arises from simplicity, how the universe explores possibility space, or it might tell us that we've overestimated the significance of this particular comet and this particular moment, that Mars remains Mars and our robots remain tools. Either answer is valuable. Either answer moves human understanding forward, but I don't think we're going to get the second answer. I think when we look back at this period 5 or 10 years from now, we'll see late 2025 and 2026 as the moment when multiple lines of evidence converged: interstellar object detection, spectroscopic anomalies, rapid robotic exploration timelines, AI-driven optimization. We'll see this as the moment when humanity's expansion into space stopped being purely about visiting empty worlds and started being about encountering chemistry that's already there, already complex, already waiting for the right trigger. And we'll recognize that the trigger wasn't geological or climatological. It was us, bringing technology and energy to a planet that an interstellar comet had quietly prepared. That's the story unfolding right now. That's what the next 2 years will reveal. And you're here at the beginning watching it happen. Tell me in the comments where you're following this from, what questions you want answered, what you think we'll find when the robots start digging, because this isn't a story with an ending yet. It's a story we're writing together, in real time, with data coming in from another world. Let's see what Mars has to say.